Hi, my name's Bob Ettinger. As a major in the Air Force in 1973 and 74, I was fortunate enough to be in the Lightweight Fighter Joint Test Force and have an opportunity to fly both the YF-16 and this airplane, the YF-17. The YF-17 was built by Northrop, and they called it the Cobra, as you can see on the side of the nose. This airplane was first flown in July of 1974 by Hank Shoto, Northrop's chief test pilot, and you can see his name up on the side of the fuselage near the canopy. The most distinguishing feature of this particular airplane is this leading edge extension of the wing. It's kind of a four-body strake that extends the wing up alongside the forward part of the fuselage and trips a vortex flow field over the top of the wing, and it's very effective in helping the airplane turn and giving it good handling qualities at high angles of attack. So now I'm back here by the farther part, the trailing part of the leading edge extension, and you can see the engine inlet here. And this splitter is designed to keep the boundary layer around the fuselage from going in the engine. And this is where the engine is, and trying to get good clean air into the engine. As we turn around over this way, you can see the leading edge flaps. This airplane and the YF-16 were one of the first airplanes to have fully automatic leading edge flaps. And the flaps actually deflected as the angle of attack increases. So as you're maneuvering the airplane to get more lift, the leading edge flaps come down and camber the wing. You can see the big drop tanks, and to get the range and stuff that we asked for in the lightweight fighter competition, this airplane has 600-gallon drop tanks. For air-to-air combat, you would get rid of these drop tanks, and I personally have jettisoned about 20 of these things over North Vietnam. So now we're at the right wingtip, and this is the launcher for an AIM-9 missile, a heat-seeking air-to-air missile that would fit on this launcher and would be used for dogfighting with enemy aircraft. So this airplane has fly-by-wire ailerons. Back in '73, fly-by-wire technology was just beginning to come forward. The YF-16 has a full, an all-axis quad-redundant electric fly-by-wire flight control system, but the YF-17 had fly-by-wire ailerons in that the inputs there's no mechanical connection between the pilot's stick and the control surface. It's all done by electrics out to the hydraulic actuator that's located in the wing. And these also bias down for landing. They're essentially trailing edge flaps that most airplanes have. Now we're back at the tail end of the airplane, and I have my hand on the horizontal tail, or the stabilizer. It controls the airplane in pitch. And above me, you can see the diagonal tails. There's actually two vertical tails, and they have rudders, the movable surface on the trailing edge of the vertical tails, and these tails are canted outward to help reduce the radar cross-section, although it wasn't very important in those days. It also gives the airplane a little more stability at high angles of attack because the fuselage doesn't block as much flow over the vertical tails. So I'm standing back by the horizontal tail of the YF-17, and as you look above me, you can see the diagonal vertical tails, and you notice this says F-18 prototype. And while the lightweight fighter competition was going on for the Air Force, Congress came along and said to the U.S. Navy that they had to buy one of the airplanes from this lightweight fighter competition. And the Navy was very interested in having twin-engine airplane because they had the extra hazard of taking off and landing from aircraft carriers, and if you had an engine problem, you'd be in the water in a big survival situation. So they wanted a twin-engine airplane, and they chose the YF-17 to go forward as their airplane. And you see the words on the tail says F-18 prototype. The Navy chose the airplane, the YF-17, to be their airplane, and they chose to change the number to make it an FA-18, which is F for fighter, air-to-air type airplane for the Navy, and A for attack, which is air-to-ground type airplane for the Navy. So we're standing back to the tail end of the airplane, and my hand is on the horizontal tail, controls the airplane in pitch, and you can see it's a pretty large surface, perhaps the size of the wing on a small airplane. Here's the engine. There were two prototype engines in each airplane, and the engines were built by General Electric. They were called the YJ-101 prototype turbojet engine, and they provided 13,500 pounds thrust each. So the combined thrust, is 27,000 pounds of thrust, and the airplane weighed about 26,000 pounds. So it had a better than 1-to-1 thrust-to-weight ratio at takeoff with a full load of internal fuel. And both the YF-16 and the YF-17 were hot-performing airplanes. And you can imagine what a rare opportunity it was for somebody like me, a junior officer, to be one of the 6 Air Force pilots that were involved in the gathering the information to help the Air Force choose the YF-16 and then the F-16. And we did all the test work for the Navy, and they ended up choosing the YF-17 to become the F-18. Okay, we're standing at the back of the airplane here, and you can see the diagonal vertical tails. And these tails are slanted outboard, which gives the tail more airflow at high angles of attack when the fuselage is normally blocking flow over the tail. And a single center tail might be blocked out by the fuselage at high angles of attack. Okay, another feature of the YF-17 was the slope-back seat. A conventional jet aircraft normally has a 13-degree slope-back of the seat, and this airplane has a 17-degree slope-back. Doesn't sound like much, but that increases the pilot's G tolerance and his ability to maneuver the airplane at higher G level. All right, on YF-17, being a prototype airplane, we had a nose boom, and that's what this is. And the idea is to have the pitot tube for the airspeed indication way up in front in the undisturbed air in front of the airplane. And the radar for an airplane would normally be behind this radome here. And in a production version of this airplane, the FA-18, there's no nose boom on the airplane. It's just the nose comes around here and comes around the radome for the radar. You can also see a little strake up here that serves kind of the same function as the leading edge extension, in that it trips a vortex here and helps give airflow over the top of the wing and stabilize the airplane at high angles of attack. As we look back, you can see the opening for the gun. In the center of the fuselage here, right up here, is where the gun was, and it was pointed 3 degrees up from the long axis of the airplane. So in a dogfight, when you're maneuvering with another guy, the gun was actually drawing some lead, if you will, by pointing 3 degrees above forward of the long axis of the airplane. You still had to point ahead of the guy in order to hit him, but because of the bullet drop and all that sort of thing in a maneuvering fight, but you had an air-to-air gun sight that had a moving reticle that computed all that lead for you, and then you maneuver the airplane to put this reticle right on the other guy and squeeze the trigger, and he blows up. Okay, to go back in time and think about what happened when it was time to buy a new this fighter as a new airplane. The U.S. Air Force had not had a new fighter of its own since the Century Series airplanes, the F-100, the F-102, 104, 105, 106 sort of airplanes. So it's been about a 30-year period there. And the U.S. Air Force chose to buy another new fighter called the F-15. And they had a big competition for this thing, and they were very, very careful to make it an air-to-air airplane, and they were very, very careful to make sure it got through the acquisition process and didn't have any problems. And they took only two technology risks with that airplane. One was a high thrust-to-weight engine, actually two high thrust-to-weight engines that gave a lot of power for their weight, and then an advanced radar. And all the other parts of the F-15 were standard state-of-the-art technology that were equivalent to what was in the F-4, which was the fighter the Air Force was using, and the one I flew in North Vietnam that had been a hand-me-down from the Navy. During that competition, a couple of companies had proposed advanced new state-of-the-art lightweight technologies and fly-by-wire things and all kinds of four-body strakes and leading-edge extensions and all that sort of stuff. But the Air Force was being too conservative, and they really wanted to make sure that nothing happened to the F-15 acquisition. So a couple of years after the F-15 program got started, they decided to take a look at some exciting new technologies. And they had a prototype demonstration program where two companies were chosen, General Dynamics with the YF-16, which was a single-engine fighter. It had the same engine as the F-15, so that was convenient for them. And the Northrop had proposed the YF-17, a twin-engine airplane. So each contractor had about 2 years to build their airplanes, and then we had a fly-off. And the fly-off really started off as an independent technology evaluation of the two different prototype models. And we were to evaluate against the same standard. And the standard was kind of a new way of doing things. They said you don't have to abide by any military specifications or anything. You had to build an airplane that would do one combat-relevant task. And that combat-relevant task was to be able to arrive at the combat arena with a clean, full fuel airplane, like you just jettison your drop tanks, and had a full load of internal fuel. And then you had to accelerate from 9/10 Mach to 1.6 Mach as fast as you could. And then do 4 max power sustained turns, level turns at 30,000 feet at 0.9 Mach. And then 3 more level sustained turns at 30,000 feet, but at 1.2 Mach. These are 360-degree turns. And you're in afterburner the whole time, so you're burning a lot of fuel. And the quicker you get around the turn, the less fuel you burned in the combat, and then the more fuel you had for cruise. At the end of that simulated combat, which took care of the acceleration and 4 subsonic turns and 3 supersonic turns, you had to climb from 20,000 feet to your cruise altitude and cruise 500 nautical miles and still have an IFR landing reserve, an instrument flight rules landing reserve, which is roughly 2,000 pounds of fuel. Enough for a half hour or so of flying once you're at low altitude getting ready to land. And that was it. And there were 7 different companies that made 8 different proposals. Northrop proposed both a single-engine airplane and a twin-engine airplane. And after evaluating those proposals, the Air Force chose General Dynamics to build the YF-16, and Northrop then to build the YF-17. And the results of that are the F-16, which is probably the best, most exciting fighter in the world for the last century or so. And they've built over 4,500 F-16s, and there are like 29 different countries that are flying F-16s. And the YF-17 became the FA-18 for the Navy, and they've built over 2,500 FA-18s, and about 8 different countries are involved in the acquisition of FA-18s. So it was a pretty successful program. Now, whenever I have a chance to talk about the lightweight fighter program, somebody always asks about the inadvertent first flight of the YF-16, and it's been on eBay and all of the networks, social networks and stuff. You can see this picture of the airplane dancing back and forth on its wings, its landing gear, and then lifts off, rocking the wings back and forth. And the pilot, Phil Ostreicher, who was the General Dynamics chief pilot, was trying to feel the lateral response of the airplane while it was rolling down the runway. And as he approached his aim speed, which is 125 knots, just about the normal rotation speed for an airplane like the YF-16, he couldn't feel any response. The YF-16 has a fixed stick, and so it's just measuring the force you apply to it. So he didn't quite realize he was getting no response. The airplane was not rocking. He couldn't feel anything. So subconsciously, he's increasing the pressure on the stick, and he had rotated the nose up in the air, and thought, well, I'll get the airplane just a little bit lighter on its landing gear, and he rotated just a little bit more. And while he was doing that, he had superimposed this roll command, which at that time was almost 50% of the roll rate that you could command. So it was 100 degrees per second roll rate that he was commanding when the airplane came airborne. And immediately it rolled rapidly over like this, and the little rotor on the elevon of the AIM-9 missile actually hit the concrete and made little marks in the thing. I could see the marks in the rotor on the elevon on the missile. And then, of course, he reacted violently back over the other side, and the airplane rolled rapidly this way, and the right horizontal tail hit the runway and knocked off a triangular portion about 8 inches on a side. And then the airplane had yawed so much, and the airplane had excellent visibility. It had a big canopy and a low canopy rail on each side, and you could see a lot better than you could out of most fighters. And when he kind of looked up, the airplane had yawed about 20 degrees to the runway heading, and all he could see was desert out there. So he figured, well, the best thing to do is push forward on the power and lift off and try to take off before he got to the edge of the runway, which he did. And as he took off, he's still rocking back and forth in what we would call a lateral pilot-induced oscillation, a PIO. And once he got clear of the ground and could kind of relax a little bit, he let go of it, and the airplane kind of steadied out and stopped rolling back and forth. And the flight control system was behaving like it's supposed to. And we called him on the radio. I was standing right beside the runway watching this thing. It's pretty exciting. We said, there's no rush to land. We can get a chase airplane airborne, and you can fly formation against the wing of this chase airplane and feel out the lateral response to the airplane before you have to come back and land. But he said, it feels, once I'm clear of the ground and I'm not stirring the stick around, it feels much like the simulator, and I think it's okay to come back and land. And we all said, well, okay, if that's what you feel like. And he came around and made a perfect landing, no problem at all. And I ended up conducting a study on what happened and what we should do about it, and end up going back to Washington to brief the 4-star general on that part of the program. But we took a month off and then went back to flying.